We now know how to analyze a single capacitor. Again, as I told you, what does it mean analyzing a single capacitor, one capacitor? Once you know those three parameters, that's circuit trinity, C, Q, delta V, once you know those three parameters, you can say that you know everything about that particular capacitor, right? So now next step, of course, logically, what if you have more than one capacitor? What if you have two, three, I don't know, hundreds of capacitors? How can we analyze them? Again, what does it mean analyzing the capacitors? If you have several of the many of those, you need to know these three parameters about each of those capacitors. So if you have two capacitors, you need to know six parameters: CQV, CQ delta V for the first one, CQ delta V for the second one. If you have three, of course, you need to know 9 parameters. If you have, so you got the, pretty much, you got the idea. And here, we're going to restrict ourselves to special situations. When you have several capacitors, and they're all connected either in parallel or in series. Right now, it might be not clear what does it mean in parallel, what does it mean in series, but when we start discussing them, I will tell you which sort of physical test, physical from the point of view of physics, you have to run in order to convince yourself that these capacitors are actually connected in parallel or in series. Because right now it looks like so they just sort of graphically parallel to each other. So they are parallel. Those guys, one after another, they're in series. Right? So actually we have a test, physics test, which you have to run in order to convince yourself or somebody else that they are connected this way or that way. Right. And again, we're going to develop a method of an equivalent capacitance. And that method, again, can be used only if capacitors are connected either in series or in parallel. Limited number of applications, but still there are plenty of situations where this can be used. Okay, so now, what's the idea behind this method of an equivalent capacitance? The idea is this. So here in the first picture, we have a bunch of capacitors. Okay, 3 connected like this, right? So the idea is we need to replace these 3 capacitors with a single capacitor, which we are going to call the equivalent capacitor, or an equivalent capacitor, right? And when you do that, when you replace this bunch of capacitors with a single capacitor, the rest of the circuit, in this case, it's just a battery. The rest of the circuit is just a battery. The rest of the circuit must work in exactly the same way. Because in real life, it can be more complicated than just a battery. You can spend weeks or days building the rest of the circuit. And when you replace those capacitors, you don't want to destroy the work of the rest of the circuit. So the idea is when you do this replacement, the rest of the circuit, the work of the rest of the circuit must not be touched, must not be disturbed. That's how we are going to develop this method of an equivalent capacitance. It's an important part of this description of this method. The rest of the circuit must work in exactly the same way. Right. Okay, so now for the next couple of slides, we need to actually derive the formulas which can be used to find that equivalent capacitance. And also, we will have to add one, for each case, important pieces of physics. And then using, for a parallel case and for the case when they're connected in series, and then those important pieces of information we will use to actually analyze actual circuits. Right. Most likely, problem we will discuss next class tomorrow. Right. But first, let's derive what needs to be derived, right? And introduce what needs to be introduced before we can actually start analyzing a real circuit. Okay, so let's start moving, or continue moving. So first, let's discuss capacitors which are connected in parallel. And let's imagine some situation. For example, these three capacitors. You see C1, C2, and C3, they're connected like this. And actually, they're connected in parallel. But I will tell you what does it mean when elements are connected in parallel. And they're connected to this battery. Actually, I didn't say, we just discussed the work of the battery, but I didn't say that the symbol of the battery is this. You see two bars, and one bar is longer than the other one. So the longer bar, the longer line represents the positive electrode of the battery, of a battery. And of course, the smaller electrode represents the negative electrode of the battery, right? So that's, let's say, the circuit which we want to analyze, right? And so that's the real circuit, right? Which we want to analyze. And so the how does this method work? You remember I told you we need to replace these three capacitors with a single equivalent capacitor. So we can introduce what is called an equivalent circuit. In an equivalent circuit, we have only single capacitor, which we called, as I said, C equivalent, which replaces these three capacitors. And again, as I told you, a very important statement, when you do this replacement, the rest of the circuit, in this case is just the battery, must work in exactly the same way. It means what? It means that if in this real circuit battery provides potential difference delta V, exactly the same delta V must be in the equivalent circuit. If some amount of charge is taken from this battery in the real circuit, let's say 5 coulomb of charge left, exactly the same amount of charge must leave battery in the equivalent circuit. It's very important. The rest of the circuit must work in exactly the same way, must not be disturbed. Okay, so that's beginning. And now, again, we're analyzing capacitors. So you remember that circuit trinity, C, Q, delta V. We need to analyze these three parameters, right? C will be at the end, because eventually the goal of this slide is to derive the formula which can be used to calculate C equivalent. Most of you know that formula. But I want to go through the derivation, because during the derivation we need to discuss physics. We need to understand what happens over here in this situation. So C will be at the end. So now Q and delta V. Which parameter should we use at the very beginning? You know what? Let's start with. Okay, I want to say with what I want to start, but let me ask you this better this way. Look, which parameter is exactly the same for all these three capacitors? Let me start with this better. I realized just at the right moment I realized, so I need to start slightly different, in a slightly different way. Which parameter out of those three, PQ delta V, is exactly the same for these three capacitors? And after our discussion of that conceptual question before the break, you should be able to realize, and even you should be able to justify why is it true. It's a potential difference. Potential difference must be exactly the same across these three capacitors. Delta V1 must be equal to delta V2 and delta V3. Why? Because I can give you the same justification. Look, this electrode of the battery, it's a piece of metal, is connected to this wire, which is a piece of metal. Then that wire is connected to that electrode of the capacitor. So then it's also connected to this electrode of the capacitor number 2. Then it's also connected to the electrode of this capacitor number 3. So for electrons, this side is just one gigantic piece of a metal. And of course, when these capacitors are fully charged, this piece of metal is in the electrostatic equilibrium. And it means all points inside of that piece of metal must be at exactly the same potential. It means that if this is, for example, 9-volt battery, and this this electrode is at plus 4.5 volts, it means that this electrode of this battery is at plus 4.5, plus 4.5, plus 4.5. And now I can give you exactly the same arguments about this right-hand side of the circuit, about this negative side of the circuit. Again, minus 4.5, then this electrode is also at minus 4.5, that electrode is also at minus 4.5, and that is at minus 4.5, right? So as a result, what's the potential difference? Plus 4.5 minus 4.5, 9 volts. Exactly the same story here. Plus 4.5 minus 4.5, 9 volts. And here exactly the same. Plus minus 9 volts, right? So you see, so pretty much what I just told you, it's the test that you have to run in order to convince yourself, somebody else, that the elements are connected in parallel. And it doesn't matter which battery you attach here, and it doesn't matter what you attach over here. If you don't change this part of the circuit, potential difference across these elements are going to be exactly the same all the time. Not just by accident under certain conditions, no, all the time. So that's what basically it means. That's what you have to say in order to convince yourself that elements are connected in parallel. When potential difference across an elements stays the same all the time, those elements are connected in parallel. You can apply it not just for capacitors. Also, in a few classes, we will apply the same for resistors. If potential difference across resistors stays the same all the time, they're connected in parallel. If you attached motors, exactly the same, so parallel. I know you can connect them with people, right? If the potential difference stays the same, right? So they're in parallel. Again, from the physical point of view, they are connected in parallel. Potential difference in this case is exactly the same. Now we need to extend these arguments and connect somehow potential difference across an equivalent capacitor. And here's the argument. So delta V1 equals to delta V2 equals to delta V3, and obviously it is equal to the potential difference provided by the battery, right? So now you remember those magic words. When you introduce this equivalent circuit, the rest of the circuit must work in exactly the same way. It means that the potential difference across the battery in the equivalent circuit must be the same. Again, delta V. And now in this inequivalent circuit, all this potential difference is across C equivalent. So potential difference across equivalent capacitor is exactly the same as the potential difference across this, across that, and across all these three capacitors. So now we can connect and we can say that the potential difference across an equivalent capacitor equals two potential differences across capacitors connected in parallel. We are going to use this important piece of physics analyzing the circuits. But for now, let me add to this line of delta V, delta V, delta V, that it's okay, so let me open first on the picture. So that those are delta V's. Here exactly the same delta V, right? So and now I can add, you see? Okay. It is equal to delta V across an equivalent capacitor. So this part, you see, I framed it. That's what we will use. And that's what I told you, that the potential difference across an equivalent capacitor equals to the potential difference across capacitors connected in parallel. We will use it. And most of the time, students forget about this. And on the exam, they write something which doesn't make much sense, right? But we will practice. We will see that it's not that bad. Okay, so now we know information about delta V. So now we have two parameters left. Remember, out of that circuit trinity, we have charge and capacitance. Capacitance, that's our goal at the end because we want to find the formula for C equivalent. So it means that let's look at charge. What happens with the charge in this circuit? So let's assume that charge Q, it's a total amount of charge which is taken from the battery. Where does this charge go? Okay, there are only three places. Some amount of charge will end up in the in this electrode of the capacitor Q1. Some charge will go into this capacitor Q2, and some charge will end up in the capacitor Q3, right? And of course, what can we say about these charges and this total charge Q? We can use conservation of charge. Q, this total charge, must be equal to Q1 plus Q2 plus Q3, because charge just cannot park somewhere over here in the rest area and forget about your the physics, right? I'm going to have a rest here. No, it's impossible, right? So if charge leaves this battery, it will end up in one of those capacitors. So we can use conservation of charge, which we already stated right in the beginning of this course. So Q equals Q1 plus Q2 plus Q3. Okay, great. You know what I like about this? Now we have an expression. So it means that we can use this expression to actually derive the formula for capacitance. Because this information about delta V's, yeah, it's a very important, but it's not an expression, right? We cannot get from here a formula for C. So now we have something. So now we just need to introduce in this expression somehow values of capacitances and see what will be the formula. So how can we insert into this expression capacitances? We can use definition of capacitance. We're going to use that formula a lot, right? That C equals Q divided by delta V here. C equals Q divided by delta V. Definition of capacitance. We introduce it today. Okay, so now we need to get Q's. Okay, solve it for Q. It's C times delta V. So Q1 equals C1 times delta V. And you see, I didn't add subscript 1 because I used the fact that all these potential differences are the same. So I dropped that subscript immediately. Then exactly the same I can write, okay, not exactly the same, similar thing I can write for Q2. C2 times delta V again without subscript, and Q3 equals C3 times delta V. So that's what I'm going to plug to the right-hand side of this expression. Now, what about left-hand side? The total charge. So how can we get the total charge? And again, somehow we need to insert now here C equivalent. Okay, so in order to get information about the total charge, let's use equivalent circuit. And in the equivalent circuit, of course, you remember, the rest of the circuit must work in exactly the same way. So if delta V here, exactly the same delta V must be over here. If charge Q is taking from the battery, in the real circuit, exactly the same amount of charge must be taken from the battery in the equivalent circuit. So now we know, and of course, where does this charge Q go? Of course, since there is only one equivalent capacitor, of course, it all end up in our equivalent capacitor. So now we can use the same formula, C equals Q divided by delta V for that capacitor, because we know the potential difference across C equivalent, we know the amount of charge in the C equivalent, right? So we can write Q equals C equivalent times delta V, because now this is a trivial circuit. You cannot make it any simpler. So now this expression for the total charge, we're going to use in our expression, right? So instead of this Q. So now derivation is almost done. So now we just need to insert all these ingredients into this expression, and we will end up, right? So instead of Q, C equivalent times delta V, and instead of those Q1 and Q2 and Q3, we have those. And you see delta V is exactly the same throughout the whole expression. Okay, so delta V can be cancelled, and we're getting the formula, which can be used to find the value of an equivalent capacitance when capacitors are connected in parallel. Okay, all right, I was planning to cover even the next slide, right, which is about capacitors connected in series, but it looks like, yeah, we'll have to do it tomorrow. And the example also will be discussed tomorrow. So from this slide, what do we need to remember? Of course, the formula. We will use it, of course. And usually students have no troubles using these formulas. 100%, okay, not 100, maybe 99% use formulas to find C equivalent correctly. But this piece of physics in this case, that potential difference across an equivalent capacitor equals to the potential differences across capacitors connected in parallel, that's where the troubles are. And again, when we start looking at examples, you will see. And those examples, I like those. They are so well structured. It's one of those pieces which I like about this book, that Knight managed to structure that problem so nicely, a solution of that problem, right? Now in series, again, so let's assume that we have three capacitors, and now they're connected like this. Right, C1, C2, C3, right? And of course, they're connected to a battery, right? So this is the real circuit. And according to our method, we need to introduce an equivalent circuit, and instead of those three capacitors, we need to introduce a single equivalent capacitor, right? So this is the equivalent circuit. And again, as I told you, you remember, when you do this replacement, the rest of the circuit, in this case, is just a battery, must work in exactly the same way in your equivalent circuit. It means that if potential difference across the battery over here is delta V, exactly the same delta V must be over there. If a certain amount of charge is taken from the battery, let's say 5 coulomb of charge went to charge those capacitors, exactly the same amount of charge must be taken from your battery in the equivalent circuit. So the work of this battery must be exactly the same, right? Okay, so now, again, since we are working with capacitors, we need to think about that. You remember three parameters, C, Q, delta V, and we're going to analyze them one at a time. And let me ask you first, C, capacitance. That's our goal. We need to find information about capacitance. So it's a question basically between charge and delta V. Which quantity, which parameter is exactly the same for all these three caps, for all these three capacitors? Which parameter is exactly the same? Usually, some students know the answer and they tell me, but often they have troubles justifying it. Some students, yeah, they just panic and who knows, right? What is exactly the same. But actually, let me give you explanation. Let me sort of guide you to the correct conclusion. So, in order to guide you, let's look at this part of the circuit. You see this red dash line, a red square, not square, damn it, rectangle, right? So where we have only what this electrode, sort of the right electrode of the first capacitor and the left electrode of the second capacitor. Let's look at this part. So what can you say about this part of the circuit from a point of view of an electron who travels through this circuit? You imagine yourself, you are being an electron, and what can you say about that? It can sound confusing question, right? But look, you're an electron, and from your point of view, what is this between the plates? It's a gap, either filled with vacuum or some dielectric material. But anyway, it's a gap. So for an electron who is, for example, on this electrode, it's an abysmal abyss, which this electron can never jump through or jump over, right? So it's basically territory which electrons cannot pass, right? And of course, we're not talking about quantum mechanical effects where electrons can tunnel through the barriers. No, these distances between the plates are gigantic, right, relative to the distances where tunneling effects can be used, right? So here, electron cannot get through this gap. Again, it's a... Then, what about this gap on this side of the territory which we're discussing, right? It's exactly the same. It's abysmal abyss. Basically, again, electrons cannot jump over that gap also because, again, it's a vacuum or dielectric material. So effectively, from electrons' point of view, this is just an island in the middle of the ocean, which cannot be reached if you want to reach it from a mainland. And also, if you are on the island, if you are an electron on the island, you cannot escape from the island. You're trapped on that on this small part of the circuit, on this section. It's completely isolated, right? So now it means, yes. So then what else can you tell about this part of the circuit? Very important piece of information from the point of view of a charge. What can you tell about the total charge in this island, of this island? If you hesitate with your answer, think this way. Let's start from the very beginning, when there is no current in this circuit. Let's assume that here there is a switch. The switch is initially open. So what will be the total charge in the whole circuit? The total charge will be 0. Every part of the circuit will be electrically neutral, right? Because the switch is open. And as a result, of course, that island is also electrically neutral. But when you close the switch, electrons start running, current starts flowing, right? And what can you tell about the total charge of that island? It will be still electrically neutral, because electrons can travel in this part of the circuit, but none of these electrons can reach that island, because again, it's like an island in the ocean, and no one can swim to that island, right? So this part of the circuit is going to be electrically neutral all the time. Okay, now once we know all this about this island, now let's try to follow electrons. So we close the switch, and of course, let's assume that some amount of charge Q started drifting that way, right? After we close the switch. So how far will this charge manage to go? Not much, not that far. It will just come to this electrode of the first capacitor, and after that, it's a gap. So pretty much all this charge will just get together at this electrode without being able to move any further, right? So as a result, this electrode is going to be charged with plus Q. Then, now, what will be the response of those electrons? Again, this island is electrically neutral, but it doesn't mean it doesn't have electrons. Because it's just electrically neutral, it means that it has equal amount of positive charge and negative charge, right? So it has still tons of electrons, right? Because it's a piece of metal. So what will be the response of those electrons once they see that this electrode is positively charged? Of course, they start feeling force of attraction, right? So of course, as a result, electrons will run to the left, to this electrode, right? There you go. Positive and negative charges, they attract. And since these two electrodes, right, so they're kind of close to each other, right? So the amount of charge or negative charge induced on this electrode will be exactly the same in absolute value as the amount of positive charge on this electrode. So it means that this electrode is going to get minus Q. So this is an induced charge. So pretty much electrons will run to this side at exactly the same amount of charge in absolute value. Then, okay, so now we know that this electrode is charged with plus Q, this is with minus Q. Then what will happen with the total amount of charge on this electrode, on the opposite side of the island? If electrons run to this side of the island and the whole island is electrically neutral, then of course plus Q is going to be on the opposite side of the island, right? So it means that on this electrode, we're going to have plus Q. So again, minus Q plus Q is going to give you 0, electrically neutral, right? So basically, we polarized this island, right? So one negative charges on that side, positive charges on that side, right? Separation. All right, so now next, let's continue this process. So now this electrode is positively charged, and of course, again, this gap is small. Of course, exactly the same amount of charge, but with opposite sign, it means that negative charges are going to be induced on this electrode. So minus Q. And again, so this part of the circuit, again, it's sort of like an island, like this one. This island is in exactly the same conditions as this one. Again, so this island is electrically neutral. Also, if minus Q is induced on this electrode, then plus Q will be left behind on the other side of this island. So that electrode will be charged with plus Q. All right? And then, so the last piece, okay, that electrode, of course, that electrode is physically connected to the battery. Of course, that electrode will be charged with electrons which will run from the negative electrode of the battery. So that electrode of the last capacitor is going to be charged with minus Q. So you see what happens? All these capacitors are charged with exactly the same amount of charge, Q. So which parameter is exactly the same for all capacitors connected in series? That is a charge. All right. Okay, so and that is basically the test that you have to run quickly in your head in order to convince yourself or somebody else that capacitors are connected in series. That's the major feature. If you see that charges are exactly the same in the capacitors, not just by accident under certain conditions, all the time, it doesn't matter what you do here with the rest of the circuit with this battery. You can change this battery. Maybe you can add additional battery. You can do maybe something else, right? But it doesn't matter what you do. Doesn't matter what you do here, the amount of charge in each of these capacitors are going to be the same, then we can say that these capacitors are connected in series. That's basically the definition of capacitors connected in series. Charges must be the same all the time, not just by accident under certain conditions. Okay, so now we can write this, what I just told you. So Q1 equals to Q2 and equals to Q3. And I wrote that it is equal to the total amount of charge taken from the battery. Okay, great. So that's the first very important piece of information. But now let's connect charges in these capacitors with the charge in the equivalent capacitor. And we're going to connect it like this. Okay, just now we came to this conclusion that charges in all these capacitors equals to charges to charge taken from the battery. But also at the same time, I told you that in the equivalent circuit, that battery must work in exactly the same way. It means that exactly the same delta V and exactly the same amount of charge must be taken from the battery. Now, where does this charge go? To equivalent capacitor. So all this charge, because we have only one capacitor, so all this charge will end up in our equivalent capacitor. So it means that the charge in the equivalent capacitor equals to this charge, equals to this charge taken from the battery, and equals to all these charges in these capacitors connected in series. So now I can add to this line of equal, equal, equal. So it is also equal to the charge in the equivalent capacitor. So now this important piece of physics, we need to remember that the charge in the equivalent capacitor equals to charges in capacitors connected in series. We're going to use this piece of physics when we start analyzing actual problems. Okay, I hope I explained to you what happens. So now, what's left? Again, out of three parameters, we analyzed charge. Now, again, capacitance will be at the very end because we need to derive the formula for equivalent capacitance. So now we just need to look at delta V. And with delta V, it's very simple. Usually students have no troubles seeing that. So the total voltage drop across the whole circuit, which is provided by the battery, delta V, equals to potential drop across the first capacitor plus potential drop or voltage drop across the second capacitor and plus potential difference across the third capacitor. So we can write, it's sort of like you remember, in order to justify it, we derived or introduced the electric potential from the potential energy. And let's use gravitational analogy. Like if you go to Olney Hall in the North Campus, right? So what you do, you take the elevator to the fifth floor, you gain potential energy. It's like a total change in the potential energy, right? Delta U1, I mean delta U total. And then you start walking down, right, stairs. From the 5th floor to the 4th floor, it's a delta U1. Then from the 4th to the 3rd, delta U2, then plus lower and lower, right? Also, then if you add all these delta U's, it will be equal to the total of voltage, not voltage, potential energy gain when you were in the elevator. So delta U equals to delta U1 plus delta U2 plus delta U3, delta U4, right? And then again, in order to get to this potential, so how did we get the potential, electric potential from the potential energy? You just take the potential energy and divide it by the charge. So if you divide it by the charge, you will get what I just told you, that delta V total equals to, must be equal to delta V1 plus delta V2 and plus delta V3. Okay, so, and what is great about this expression, because now it's basically an equation, and using this equation, we should be able to derive what we wanted, formula for equivalent capacitance. But of course, we need to replace these delta V's. We need to somehow insert in this equation capacitances. And that can be done easily because you remember the formula for the capacitance. C equals Q divided by delta V, previous class. So now we need to solve it for delta V. So delta V goes up here and C goes downstairs. So delta V will be equal Q divided by C. And that's what we will use to rewrite this equation. So delta V1 will be equal Q divided by C1, delta V2 exactly the same but divided by C2, and delta V3 Q divided by C3. And you see there are no subscripts next to Q's. I used immediately the fact that all charges are the same, right? So that's what I'm going to use in my right hand side. You see, the steps in this derivation are very similar to the steps which we've made in the previous class yesterday. And we actually, when we're going to derive similar expressions for equivalent resistance, and again, a structure of the slides will be exactly the same, right? Just easier to remember if you keep structure the same. But anyway, so now what about the total potential difference? How can we write an expression for total potential difference? Use an equivalent circuit like we've done in the previous slide. You can check that slide, right? This charge Q is in the capacitor. Then potential difference provided by the battery is also across that capacitor, because there is nothing else across this battery, only that charge. So as a result, we can write that this delta V, again using this formula for the capacitance, right? So C equivalent in the equivalent circuit equals charge in the equivalent capacitor divided by the potential difference. So we can write that delta V equals charge in the equivalent capacitor, which is equal to the charges, these charges. So that's why, again, there is no subscript next to Q, divided by C equivalent, which we want to find eventually. So that expression from the equivalent circuit, that's what we're going to use instead of this delta V on the left-hand side. So basically almost done. So once you plugged all these Q's divided by C's, you will end up with that. Since Q's are exactly the same, they can be cancelled, and we're getting the formula, which most of you know. All right, but I didn't feel like just presenting this formula because we need to discuss physics. What happens? Especially, we needed to discuss the fact that charges are the same. Right, and this is not that obvious, right? And that's why I go through this derivation, because of this significant amount of physics which needs to be discussed. Okay, so what do we need from this slide? Again, formula for the equivalent capacitance, and usually students have no troubles applying this formula, right? I know 99% of students use them properly, except for occasionally, typical mistakes, guys, warning you. They calculate these reciprocals, add them up, and they claim that this is C equivalent. No, it's a 1 over C equivalent. So you need to still flip it, and they get the number, they get excited, okay, almost done. So they jump and forgot to make the final step, right, the last step. So almost every semester I see those silly mistakes which are not needed. Right? So don't forget to flip, right, in order to find the value of C equivalent. So we need to know that, and of course we need to remember that fact that charge in the equivalent capacitor must be equal to charges in the capacitors connected in series, right? That's where students have troubles applying this every semester. Like, I know maybe like 30% of students, they just write something which, I don't know what that, but it happens. But no troubles applying those formulas.